Alright, so welcome to the CS for Future Review Session Spring 2017. If you're watching sometime in the future, like 2018, 2020, I'm glad this is still relevant. So I'd like to thank Koa, who is behind the camera, hopefully behind the camera in a few minutes. And I'd like to thank David and Navy for getting us the pizza. So before we begin, I'd just like to quickly go to the review sheet and go over what the exam is on. So the exam will cover everything from the beginning until the random number lecture, which is the same lecture as the confidentiality using symmetric encryption. So it'll be everything from that to this inclusive, okay? So the best way to prepare for this is, of course, going through slides, handouts, and watching this review session. If this wasn't useful, we wouldn't be doing it. And if you're able to answer the questions on the handouts, if you understand the main concepts, you should be good. Most importantly, learn how to solve problems. Can you apply the things we learned in class in order to solve a problem related to what we covered? So the test will be primarily short answer. Maybe sometimes a multiple choice or two sneaks in, but generally it's a short answer. Or a solve this problem kind. Encrypt this, decrypt this. Explain this. Show that. Basically, that's the basic idea. So with that said, one suggestion which I was given last year is to start with DES and block cipher principles, then work our way down to AES, then to block cipher modes of operation, and then jump back to introduction and classical, because I think that's the part with which people have most questions. And I think everyone's here has unanimously voted in favor of that, right? Is that still the case, or yeah? Okay.
Yes.
Yeah. All right. So with that said, let's get started. So, and by the way, I put up the review sheet in both Word and PDF formats. So in case you like to take notes in your computer, I hope you find that useful. All right. So let's get started with block ciphers. So the first question asks us on the handout, what is the difference between stream and block ciphers? Well, so this gets right into it. So what is a block cipher? So a block cipher is something which encrypts things multiple elements at a time. Could be multiple bits at a time, could be multiple bytes at a time, but typically multiple elements at a time. So typically we say that a block cipher is an n-bit block cipher if it encrypts blocks of n bits at a time. So typically what a block cipher will do is it'll take a plain text block of n bits, transform it in such a way, and spit out a cipher block that is also n bits long. So the plain text block size and the cipher text block size are typically the same. The kinds of algorithms we talked about, the kinds of block ciphers we talked about, were either 64 or 128 bits long. So remember, DS encrypts things 64 bits at a time, and AES encrypts things 128 bits at a time. So for DS, block size is 64, and for AES, it's 128. All right. So, now, what's a stream cipher, and how is it different from a block cipher? So a stream cipher encrypts things one element at a time. Block cipher encrypts things multiple elements at a time. Typically, stream ciphers tend to be faster than block ciphers. They're also typically easier to implement, but they tend to be less secure. Block ciphers, on the other hand, they are harder to implement. They tend to not be as fast, but they tend to be very secure if you get it right. Okay? So that's basically the idea behind that. So, and many modern ciphers nowadays are block ciphers. Just a few days ago, well actually, and a few days ago means yesterday, my father asked me to send him my credit card information about, because he was doing taxes for the family, and he already bought, tax cut, so, I can save some money by, using his services, and sometimes too. So he asked me to give him my credit card number. So what I did was, I put it in a zip file with many other documents, and I gave it, a name that wasn't very, attractive. Basically, I just put in a bunch of my biometrics work manuscripts, and I added a Word file called, bibliography. So in case somebody, gets it, they want, look into that. So now, then I put all of that into a zip file, and I wanted to password protect it. So I noticed that the zip program asks me how do I want to encrypt this, and it offered me to use AES-256, and that's what I chose. So, and then I also hid the whole thing in a picture, when I sent the picture to my father, under a unsuspecting title. It was, look at how much weight it lost, so, yeah. So basically what you would have to do is, extract the zip file from the picture, then enter my passphrase in order to decrypt it, and then in the mess of files find that file. Oh, and all files were also password protected, so yeah. Anyway, so, but yeah, that's one application of block ciphers. Okay, so if you're using a cipher to encrypt large amounts of data, chances are you're using a block cipher. Okay, so disk encryption, file encryption, block ciphers work very well for that. So you get the basic difference, right? Stream, one element at a time, block, multiple elements at a time, right? So, all right. What makes a block cipher reversible? Now, a block cipher, as with any cipher, it'd be kind of useless if I would be able to encrypt but not decrypt, right? That would make my cipher very useless. Because what makes them useful is I can encrypt something, send it to somebody, and if they have the key, they can decrypt it, right? So, what makes a block cipher reversible? And we talked about that. So, what makes a block cipher reversible is a one-to-one mapping between plain text blocks and ciphertext blocks. So, here is the idea. Let's say that I have a 2-bit block cipher. So a 2-bit block cipher encrypts things 2 bits at a time, takes a plain text that is 2 bits in size, and outputs a ciphertext that is 2 bits in size. Yeah, not very secure cipher, not very practical cipher, but it serves well to illustrate the point. So now, if my block cipher is 2 bits in size, how many possible plain text blocks can I have? Well, that's basically all the possible blocks I can represent with 2 bits, right? And how many different blocks can I represent with 2 bits? Well, there are only 0, 0, 0, 1, 1, 0, and 1, 1. Those are the only possible blocks, right? So, now, my ciphertext blocks, they're also 2 bits, and this means that the number of cipher blocks is also 4, right? What a block cipher is, in a very abstract sense, is a function which takes a plain text block and maps it to some, ciphertext block. So here's an example of a block cipher. This one takes a block 0, 0, and it outputs a cipher block 1, 1. Or if you give it a 0, 1, it'll output 1, 0. If you give 1, 0, it'll put out 0, 0. Finally, if you give it 1, 1, it'll put out 0, 1. So now, in order for this to be reversible, in other words, so I can take this and I can go back to that from ciphertext to plaintext, which we call decryption. I need the mapping between those blocks to be 1, 2, 1. Why is that important? Well, let's say that my mapping is not 1 to 1. Let's say that I have something like this. Let's say that 1, 0 and 1, 1 both result in a ciphertext output that is 0, 0. Now, this is fine for encryption, but what about decryption? If I give the algorithm 0, 0 and tell it to decrypt it, well, how is it supposed to know whether it should go to 1, 1 or whether it should go to 1, 0? The decryption algorithm will have no idea. Makes sense, right? So, this is why it's important for the mapping between the plaintext blocks and ciphertext blocks to be 1, 2, 1. Or every plaintext block must map to exactly 1 cipher block. Makes sense, right? So this is what's required in order for the block cipher to be reversible. Okay, we're good? Yeah, any questions so far? Or we're good? Oh, great. So, yeah, so I guess our motto today is quality over quantity, huh? Yeah? All right. So, and that covers that. So, understand block cipher concepts, and we covered a few of those. So, the first concept which I'd like you to understand is, let's say I have a block cipher that is encrypting things, say 64 bits at a time. So how many possible plain text blocks or ciphertext blocks can I have? 2 to the 64, right? Because it's really the same question as if I ask you, how many different numbers can I represent using a binary number that is 64 bits? That's easy, right? 2 to the 64. That is any number from 0 to 2 to the 64 minus 1, right? So if I ask you how many different plain text blocks or ciphertext blocks can a block cipher have, well, that's really the same question. It's 2 to the whatever the block size is, right? So with DES, which encrypts things 64 bits at a time, the number of possible plain text blocks is 2 to the 64, right? With AES, it's 2 to the 128, right? So if one day, we get block ciphers which encrypt things 256 bits at a time, and actually I believe Reindoll, the basis of AES can actually do that as well. Yep.
You just mentioned that you had used AES 256.
Mm-hmm.
Doesn't that mean that it can encrypt 2 to the 256?
No, that means, so it still encrypts 128-bit blocks at a time, but it's the key size that is 256.
Gotcha.
Mm-hmm. Yeah. Wait, when you see AES followed by a number, it's talking about the key, because AES supports keys ranging from 128 bits to 192 to 256. So AES 128 is AES which uses 128-bit key. AES 192 is the one which uses 192-bit key, and 256 uses a 256 key. So that refers to the key, not to the block size. All AES is 128 bits in size. Yeah. Mm-hmm. Yep.
So is Reindoll an open standard?
Reindoll is, it didn't really become standard. AES is what became standard. But AES came from Reindoll.
Okay.
Yeah. Mm-hmm. So, and yeah, in theory, you could use AES to encrypt 256-bit blocks. But the thing is, it's not part of the AES. So, because AES stands for Advanced Encryption Standard. So basically, people took, Reindoll, and they took a subset of Reindoll and said, that's what's going to become the new Advanced Encryption Standard. Mm-hmm. Make sense? Yeah. Yeah, so basically, that's the idea right here. And if I have an n-bit block, then I can have 2 to the n possible plain text blocks or ciphertext blocks, right? Make sense? All right. Now, another concept which I'd like you to understand is how many mappings can I have from plain text to ciphertext if I have an n-bit block cipher, assuming we use an ideal block cipher. Now, what's an ideal block cipher? So, an ideal block cipher is a cipher which maps every single plain text block to some ciphertext block. Okay? So, and it provides all of the possible mappings, right? So, let's say that I have a 4-bit ideal block cipher. So, on this side, I have my plain text blocks, and my plain text blocks will range from 0000, right, to 0001 to 0010, etc., all the way up to 15. And that should make sense, right? Because if I have a 4-bit block cipher, then I can have 2 to the 4 different plain text and ciphertext blocks, and their values will range from 0 to 2 to the 4 minus 1, right? So now, here, if this algorithm as an input gets 0, 0, 0, 0, the output will be the binary of 15. I think. Did I do my files correctly? This is kind of hard. Or 14, I guess it's 14, yeah. those lines are kind of hard to follow. All right? But you get the idea, right? Let's try something easier. If I give it 0, 0, 0, 1, right? Then the output will be 4, right? The binary equivalent of 4. Makes sense, right? So, now, how many possible mappings can I have? Well, how do I begin to figure that out? Well, one way to think about it is this way. So let's say that, right here, I line up all of my plain text blocks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And so those are my plain text blocks, right? And a ideal block cipher maps a plain text block to some cipher block, right? Now, how many cipher blocks can I have, and what kind of cipher blocks I will have? Well, same as the plain text blocks, right? Right? They can go from 0 to 15, right? And there's going to be 16 of them. So I'll use red for ciphertext. Now, let's assume that, underneath each of the plain text blocks, I will write down the cipher block to which I want to map it to. So let's say that, 0 I want to map to 2. 1 I want to map to 3. 2 I want to map to 15. 4 I want to map to 4. Etc. So that makes sense, right? So now, dot, dot, dot. So by shuffling those numbers at the bottom, right, I can create a new mapping, right? Does that make sense, right? So now, the question on how many different mappings I can have, doesn't it simply become a question of in how many ways can I shuffle those numbers on the bottom, right? So, if I have 16 different numbers, in how many ways I can shuffle them? 16 factorial, right? That's the number of ways in which I can shuffle them. So, I get 16 factorial, okay? Now, 16 is the number of my blocks, right? Now, and if I have a 4-bit block cipher, how many different blocks can I have? So let me erase this so we can do this right from the beginning. So I have a 4-bit block cipher. How many different blocks can I have? Right here on the bottom. Huh? It's a 4-bit block cipher. Huh?
4
It's a 4-bit block cipher.
from 16.
It's 16, right? 2 to the 4, right? It gives me 16, right? So this is how many different blocks, I will have, right? Now, in how many ways can I shuffle those blocks up at the bottom? Well, if I have 2 to the 4 blocks, right? I can shuffle them in 2 to the 4 factorial, right? Make sense? So it's really a question of figuring out, number one, how many blocks do you have? And number two, in how many ways I can shuffle those blocks, right? And if I have an n-bit block cipher, the number of blocks I can have is 2 to the n, right? And the number of ways in which I can shuffle up 2 to the n blocks is 2 to the n factorial. Makes sense, right? Yep.
When you say the number of blocks, do you mean the size of the block, or do you mean the number of
I
literally?
actually mean the number of blocks, yeah. The size of the block is, so the size of the block in this case is 4 bits, right?
Right.
But the number of blocks is 2 to the 4. It's 2 to the 4 because the number of different blocks I can have with 4 bits is 2 to the 4, right? And I can shuffle those blocks in 2 to the 4 factorial ways. Does that make sense? So that's basically the idea right there. Now, why don't we like the ideal block cipher? Why is it not very practical? Well, the answer is it's because the key happens to be pretty. Oops. What's happening here? Wait, why is it going that way? There you go. why do we like using an ideal block cipher? Well, the reason is that it's not practical. It's not practical because the key size is humongous. Okay? So, and why is it humongous? Well, in this diagram right here, so all of those lines, right? The line which maps a plain text block to its corresponding cipher block, that's part of the key. And all of those lines, they are a key. Makes sense, right? So, if we were to communicate using this block cipher, I would need to tell you, bless you, what maps to what, right? So, in case I send you a block number 14, you know that the plaintext block is 0, right? Make sense? So, I would need to tell you all of those mappings. Make sense, right? So, now, how big will our key be? Well, to answer the question, let's think about how would you represent this key if I was to give this to you, right? Well, I would need to tell you, a few things, right? So, let's say that, and I will write it in you here. Let's say that you will assume that I will send you a sequence of blocks, right? I will send you a sequence of blocks, and each of those blocks will be the cipher block. So the first block I sent you, right, will be the block that corresponds to the plain text of 0, 0, 0, 0, okay, in a 4-bit block cipher. The second block I gave you will be the one which corresponds to 0, 0, 0, 1, etc. Okay? So let's say that you line up all of your text blocks, going from 0, 1, 2, 3, 4, all the way up to 15. And then we need to exchange our key, right? I need to give you the key. In other words, I need to tell you what maps to what, right? So let's say, I will give you a sequence of blocks which will tell you what maps to what. So like, for example, I give you a sequence, 2, 3, 5, 16, and I'm just making those up, okay? I will have to give you this sequence, right? Makes sense, right? Now, so how many blocks will there be in this sequence? That should be easy. For a 4-bit block cipher.
16 times.
So how many blocks can I have in a 4-bit block cipher? 16, right? So 2 to the 4, right? So I'll have to give you a sequence of 2 to the 4 blocks, right? And how big is each block?
4 bits.
4 bits, right? So now I need to multiply this by 4, because the size of each block is 4 bits. So I have 2 to the 4 different blocks, and the size of each block is 4 bits, thus giving me, 2 to the 5th. That'll be the size of my key. Okay? Make sense? So now, it doesn't look so bad for a 4-bit block, but what about if I try to do this for a 64-bit block? Well, then in this case, it'll be 2 to the 64 times 64. And how big that is? That's pretty freaking big. Just how big? Well, I think in class we did a Google calculation, right? Where we have figured out just how big this is. So, in class we did 2 to the 64 times 64. And this is how many bits my key will be. Okay, so we did that. That's how many bits there will be in my key. So, and then we went to Google, and what we did was we converted it from bits to terabytes. So if I go to Google, bits to terabytes. Yeah, so my key is going to be what is it? 1,475,000 no, it's actually 14 million. 757,000. 147 million, excuse me. 147 million terabytes, 5,703,952. That's how big my ideal cipher key will be for a ideal block cipher if we use blocks of 64 bits. That's just not practical, right? Makes sense, right? Not so bad for a 4-bit block cipher, but not so good for a 64-bit block cipher. Now, we probably, don't even want to know what that's going to be for AES, which is using 128-bit blocks. So, yeah, that's one huge key. So that's why ideal block cipher is not practical. So, just to review, the key size for the ideal block cipher is equal n times 2 to the n, right? Where n is the block size in bits, right? Make sense? All right. So that's a very important concept. So there are two important concepts here. One is how many possible mappings can I have in a n-bit ideal block cipher, and how big is the key? And of course, they are closely related. That comes out as a consequence of this. Makes sense, right? Very good? All right. So, okay. So, and there is a question. How many possible keys can I have in an ideal block cipher which encrypts 64-bit blocks? Well, we just did that, right? So, if it asks us how many possible keys, it would simply be 64 times 2 to the 64, right? And how many different mappings can I have in an ideal block cipher that encrypts 64 bits at a time?
No, 64 factorial?
Exactly. I put them together, and you're right, yeah. 2 to the 64 factorial, right? Make sense? Yeah. So that's so those are important concepts, and I heard Kat likes them very much. All right. So that's basically the idea there. Now, and this takes us right to our next question, which asks us, how does Fistel cipher perform substitutions and permutations? So this takes us right to the Fistel block cipher. Now, so the reason why we need something like a Fistel cipher is because the ideal block cipher is just not practical. N times 2 to the n key size is just, is just way too much. Okay? That's just too big of a key. We need an algorithm which will give us a smaller key size. And the beauty of the Fistel cipher is that it reduces the key size from n times 2 to the n to 2 to the k, where k is some reasonably sized number, such as, for example, for DS it's 56, for AES it could be 128, 192, or 256. So basically, the size of the key is reduced to k bits instead of n times 2 to the n. So basically, it reduces the key size. Okay, we need an approach which will reduce the key size, and Fistel cipher is exactly that. It says, hey, n times 2 to the n is way too big. Let's have our key whose size is k bits, and it'll give us a subset of all the mappings that are possible with an ideal block cipher. Okay? So, and the way that the Fistel cipher works is that it alternates substitution and permutation. Recall that substitution means replacing plaintext elements with ciphertext elements, right? And permutation means we shuffle things up. And when we talk about classical ciphers, right? Some classical ciphers were substitution ciphers. They replaced elements of the plaintext with elements of the ciphertext. For example, the Caesar cipher and the Playfair cipher. Some ciphers were transposition ciphers, like, for example, rail fence. like the row transposition cipher, right? Row transposition cipher is a transposition cipher, right? There should be no confusion about that. But the bridge to the modern world is you remember what it's called? Product cipher, right? Product cipher is a cipher which does both substitution and permutation. In other words, it replaces elements of the plain text and it also shuffles them up. So we gotta do both, okay? So that's basically the idea over here. Now, let's take a look at the Pistol cipher and how it works. One thing to remember about a Pistol cipher is that it's not actually a encryption algorithm that you can use to encrypt or decrypt something. It's more of a framework. It's more of a design pattern. Okay? Well, not a design pattern, but more of a abstract algorithm, if you will. So it lays out the framework, but it leaves a lot of the elements, unfilled. Okay? So the way that Pistol cipher works is like this. So it takes a plain text whose size is a multiple of 2. The reason we want that is because we'll take the plain text and we will divide it into 2 equal halves. And then each half, actually both halves, but separately, they'll be processed through multiple stages of substitution and transposition. So the first thing I'll do is I'm going to take my plain text and I split it into 2 equal halves. And then I do the following. So the right-hand half will go through what's called a round function. Round function is something which will replace the bits of the right-hand half with some other bits. How exactly does it do that? Pistol cipher doesn't tell you. That's up to the person who is designing an actual encryption algorithm based on the Pistol cipher is to figure out. Okay? So somehow the round function substitutes the bits of the right-hand half for some other bits. How? Pistol cipher doesn't tell us. That's for us to figure out. Okay? If we're designing an encryption algorithm based on Pistol cipher, that's for us to figure out. Now, the output of that round function, the transformed right-hand half, is then XORed with my left-hand half. And the result of the XORing then becomes my new right-hand half, and the original right-hand half becomes my left-hand half. Now, what did I just do here, by the way? I swapped my right-hand half and my left-hand half, right? So, once again, I took my right-hand half, I ran it through the round function, which replaced some bits of the right-hand half. Then I XORed the right-hand half with my left-hand half. The result of the XOR became my right-hand half of the text, and the original right-hand half has become a left-hand half. So, can you see the elements of both substitution and permutation here, right? The substitution is the round function, and the permutation is the swapping of the 2 halves, okay? Now, after this, I take my output of this, of my first stage, and then I run it through another stage, where exactly same thing happens. Okay? Makes sense, right? And I run my block of text through multiple rounds, which keep doing the same thing, which I just described. And then, at the end of the last round, I'm going to swap the 2 halves again, and comes out my ciphertext. Now, for how many rounds do I repeat this? Once again, Pistol cipher doesn't tell us this. This is up to the person who is designing an encryption algorithm based on the Pistol cipher. Also, one more thing to notice here is that each round takes a separate key. This key is necessary for the operation of the round function. So, the round function substitutes the bits of the right-hand half based on the key. How? I don't know. That's for the person designing the algorithm based on this to figure out. But the round function takes a right-hand half and a key, and somehow uses the key to replace elements of the right-hand half with some other elements. Makes sense, right? So basically, it leaves a lot of blanks. So one blank is, how does the round function work? How do we generate a key for each of the rounds? Okay? And for how many rounds do we run this processing of a block? Makes sense, right? So, and once again, substitution is the round function, and permutation is the swapping of the two blocks. So that's why we say that it alternates substitution and permutation. Makes sense, right? So, all right. So this is the formalization of the Fistel cipher, and basically for round I, the right-hand half is equal to the the left-hand half is equal to the right-hand half of the previous round, and the right-hand half is equal to the left-hand half of the previous round, XORed with the output of the round function, which will perform substitutions on the right-hand half from the previous round based on the round key, that is Ki. Okay? Make sense? Now, one nice thing about the Fistel cipher is that encryption and decryption are pretty much the same. The algorithm is exactly the same. The only difference is that in decryption, I reverse the order of the keys. So in other words, in encryption, in the first round, I provide K1, in the second round, K2, etc. In the nth round, Kn. In decryption, I do it the other way around. So in round 1, I will provide key Kn. In round 2, I provide the key Kn minus 1. And finally, at the round Kn, I'll provide the key K1. Otherwise, the decryption algorithm stays exactly the same. That's a big advantage, because I need only one algorithm to do both encryption and decryption. Makes sense, right? Right? Very good. Okay. So that's basically how the Fistel cipher works. So going back to the review sheet. So how does Fistel cipher perform substitutions and permutation? Well, substitutions is that it runs the right-hand half of the text through a round function, right, which replaces elements of the right-hand half with some other elements based on the round key. Okay? And how does it achieve permutation? Well, it swaps the two halves of the text, right? And it does that for multiple rounds. What are the advantages of the Fistel cipher network? Well, the encryption and decryption are basically the same algorithm, right? The only thing I need to do to convert encryption into decryption is to, swap the order of round keys. Basically, reverse them, okay? The key for the nth round is used in the first round. The key for the second to last round is used as a key for the second round, etc. Okay? So basically, it's the same algorithm for encryption and decryption, just reverse the order of keys as they're fed into the rounds. Okay? Know and understand how to use all DES related tables. And I think that's the most fun, right? So now we talked about DES. Yes, DES is a widely used block cipher. It encrypts things using 64 bits at a time. It's a 64-bit block cipher, and the keys are also 64 bits in size. Okay? Now, of course, we did learn that although DS takes a 64-bit key as an input, it will immediately strip away 8 bits, thus resulting in a key of 56 bits, which is actually used in the encryption. Now, we also did learn that there are some mysteries about DS. We don't know why some parts of DS are the way they are, but it doesn't mean we cannot learn about them. So, DS is based on a Fistel cipher network. So, all of that DS is, it follows the Fistel cipher, except it fills in all of the unknowns. For example, it defines how the round function works. It defines for how many rounds a single plaintext block is processed during encryption, which is 16 rounds, right? And it also defines how the key is generated for each round. And the way that the key is generated for each round is based on the original key that the user provides. So based on that key, it'll derive 16 separate keys for each of the 16 rounds through which a single plain text is processed through. Makes sense, right? So, alright. So that's basically the idea right here. So here is the structure of DES. So the way it works is, and we can look at it from two different perspectives. So on this side, we have our key generation algorithm. Sometimes it's referred to as key schedule. Key scheduling or key generation algorithm, that's the algorithm which will take a 64-bit key, and then, based on that key, it will derive a round key for each of the 16 rounds of DS. So, and then, on this side, I have the processing of my plain text through the rounds. So, the basic idea behind the plain text processing is that as an input, it takes a 64-bit block and it runs it through what's called an initial permutation. The initial permutation is just a function defined using a table which will simply shuffle up the bits of the input. Now, this function doesn't really add any security to the algorithm. This is because at the very end of the processing of the plain text, there is something called inverse initial permutation, which will undo, basically unshuffle, all of the shuffling that the initial permutation did at the end. Now, the popular explanation for the existence of the initial permutation function is that it helps, align the bits in such a way that it makes it more efficient to process the text in hardware. Because typically it will be put into 8-bit or 16-bit registers. So a 64-bit block will be put into different registers. So by doing initial permutation, it helps align the text more efficiently in the registers, so it's processed more efficiently in hardware. That's that's the most common explanation for that. After that, we take the output and we process it through the first round, which has a round function, and that round function takes our key generated for the round. And then the output of that gets processed through another round. Overall, it goes through 16 rounds. At the end of the 16th round, we swap the two halves of the text, okay? And then we run it through the inverse initial permutation, which undoes what the initial permutation did. Now, what about our key generation? So the way our key generation works is, DES takes a 64-bit key and it runs it through a function called permuted choice 1. Permuted choice 1 will strip some bits away from the key, thus shrinking a 64-bit key to a 56-bit key, and also shuffle the bits of the key up. Okay? This function is performed only once in the beginning. Okay? Then the key gets ran through what's called a circular shift function. Now, my key is now 56 bits, so the way this function works is it cuts the key into two equal halves. And then both halves independently are left circular shifted based on a special table which tells by how much to left circular shift each half based on which round you run. And then the output of that gets ran through the permuted choice 2 table, which does more shuffling and also strips the key down to 48 bits, and that goes into the round function. Okay? And then in each stage, I repeat the whole process. So I take the output of the left circular shift of the previous stage, and I run it through the permuted choice 2 function. Okay? And then the output of that becomes the key for that round. Okay? That's the high-level overview. Now, let's take a look at how the different tables work. So this is the initial permutation table. The beauty of this is that if you can understand the concept behind how this table works, you can pretty much understand how most of the other DS tables work. So let's say that this is my plain text. This is the first bit of my text, this is the second bit of my plain text, etc. That's my 64-bit of the plain text. What this table says is the following. The first bit of my output is equal to the 58th bit of my input. So what I will do is I'll take my original plain text, I'll find the 58th bit, and I will write it down as my first bit of the output. The second bit of the output is equal to the 50th bit of the input. So I go over here and I find the 50th bit and I write its value down as a second bit. Finally, and etc. For my third bit, my output value is equal to the value of the 42nd input bit. What?
Okay, so this table, it's one, the start index is based, right? So when we're given an actual table, we actually have to adjust it -1. So it's,
If you do it in Python.
Okay, yeah.
Yeah, if you do it in Python. If you assume if your table starts at 1, and you're doing this, by hand on this one specifically, right? Because numbers here start at 1 as well, right?
Right.
It's fine right here. But be careful if you do it in Python, because like if I give you this table and you do it in Python, right, which is fine, but just be sure that in Python things are 0-based, right? So when you locate the bits, you would have to subtract 1 from the number in the table.
Okay.
Yeah. Mm-hmm. Yeah.
And then this one, the output, it's going to be, is it still going to be the same size as it was originally, or is it going to be reduced?
In case of the initial permutation, yes, it's yours? Okay. In case of initial permutation, the answer is yes, because the initial permutation does not eliminate any bits. And we can see that